Hello everyone. Today I will be doing curve tracing in Cartesian format. Curve tracing in Cartesian format we shall look into. Basically, curve tracing is nothing but tracing a freehand curve. Okay, it's just tracing a freehand curve. There's a checklist. There's a checklist to draw a curve, looking at the equation of the curve, tracing a freehand curve using basic criteria. Using basic criteria or checklist. Basic criteria. Okay. So basically it will have three to four important points. Those are S, O, T, A, I, and R. S stands for symmetry. O stands for origin. T stands for tangents. Of course, these tangents I'm talking about at origin only. A stands for asymptotes. I stands for intersection. Intersection with the axis. R stands for region. Of course, there are some more things which I will talk about, but basically I'll be needing 2 to 3 points, 2 to 3 criteria to draw a curve. Now coming to symmetry. S for symmetry. What does this, how do I say a curve is symmetric? There are different criteria for symmetry about x-axis. How do I check about x-axis? I will take a basic example. I'll consider a basic example. That is y square is equal to 4ax. Okay. Now, how do I check symmetricity about x-axis is if we have even powers of y. Even powers of y in the curve equation. In the curve equation. Now, I can clearly see, many of you know that this is a parabola which has even powers of y. So, the curve would be symmetric about x-axis. All of you know that the parabola looks like this. It is symmetric about x-axis. Okay. Similarly, about y-axis. How do I say a curve is symmetric about y-axis? Again, I'll consider this basic example. X square is equal to 4ay. Again, this is a parabola. Okay. If we have even powers of x. If we have even powers of x. X in the curve equation. In the curve equation. Okay. Now, all of you know how this parabola looks like. Even powers of x, so symmetric about y-axis. My parabola looks something like this, guys. Okay. Third point would be symmetric about both axes. Symmetric about x and y. How will I say? Just see here. Even powers of x and y if I have. Even powers of both x and y if I have. Best example would be x square plus y square is equal to 4. It's a circle with radius 2. Okay. Now, what exactly is symmetry if you want to understand, guys? I would just tell you, symmetry is nothing but the mirror image kind. In mirror, if we look at ourselves, left side of ours will appear to be right and right would appear to be left. Okay. Now, if I say symmetry about an axis, if I say mirror image, if you're not clear, look at this parabola. I have this parabola, right? This parabola I'm talking about. Now, about y-axis, it is symmetric. So, about y-axis, if I flip this part, this part, if I flip, if I fold like a paper about y-axis, the folded version sits exactly on the other half. The one half, when folded about the axis about which it is symmetric, it sits exactly on the other half. That's what exactly is symmetry. You can check that. Now coming to the circle, guys. Circle, all of us know it looks like this. Okay. Now if I flip about y-axis, if I flip this paper about y-axis, then this half sits over this half. Similarly, if I flip about x-axis, this half sits over exactly over the other half. So that's what is symmetry. Or in other words, in a standard language, we will call that mirror image. Mirror image, or the axis about which the curve is symmetric is the mirror, which is placed between both the halves. And then if you look in the mirror, left looks right, right looks left. Now there's another version also of symmetry, that is symmetry about y is equal to x. Line, all of us are aware of the line y is equal to x. Okay, in polar we'll call this line to be theta is equal to pi by 4 line. Okay, yes. Now how do I check for symmetricity about y is equal to x? Simple, just interchange x with y. Interchange x with y and y with x and y with x in the equation of the curve. In the equation of the curve. Okay, so what happens if I interchange? I'll just give an example so that you understand. All of you know this example, right? This is your rectangular hyperbole. Yes, it's your rectangular hyperbole. Okay, I'll be replacing y with x and x with y. I'll get back the same equation. Hence, you know the curve of this rectangular hyperbole also. It looks something like this. You can as well say symmetric in opposite quadrants kind of things. Okay, this would be my rectangular hyperbole. Okay, there's one more which you will come across in the unit of curve tracing. One more example, that is x cube plus y cube is equal to 3xy. Okay, now please see here. I'll replace x with y with x. I'll get back the same equation. Okay, hence this curve is symmetric about line y is equal to x. Okay, fine. Now I'll just show the basic shape of this curve for you. Later on, we will see how this curve has turned up. Okay, how I'm able to draw the shape of this curve. Okay, this curve looks something like this. This is my line y is equal to x. If you just flip the one half of the curve on the other, it will exactly sit about the line y is equal to x. You have mirror images. Okay. That's all about symmetricity about the line y is equal to x. There's also symmetricity about the line y is equal to minus x. How do I find it? Let's finish off this also. This is also there. This will also be there at the end in the checklist. So what I will do, interchange x and y with minus y and minus x respectively. Respectively means what? I'm interchanging x with minus y and y with minus x respectively in the curve equation, in the equation of the curve. Okay, so see this example, xy is equal to c square. This is the best example. Okay, what I will have is minus y into minus x is equal to c square, or xy is equal to c square again. I'll get back the same equation. So this curve is symmetric about the line y is equal to minus x. Yes. After this, the next point that I will have is origin. O stands for origin. How do I check whether any curve passes through origin or not? I will just put the point, put 0, 0 and the equation of the curve in the equation of the curve. If the curve equation reduces to identity, if the curve equation reduces to identity, Okay. Identity means what? 0 is equal to 0 form I. Okay. Reduces to identity. Then the curve passes through origin. Then the curve passes through origin. Origin. Okay. We'll consider one example. Anything we can consider. Y is equal to execute. Okay. I'll be adding 0 is equal to 0. Okay. We know how the curve looks like. It looks something like this. Okay, any curve we can consider. Okay, now symmetricity is just for an information, guys. Origin. If the curve passes through origin, there's another important point called tangents at origin, which would be very much helpful to you. Tangents at origin is very, very, very important. Tangents at origin, because these decide the basic shape of the curve. How do I find tangents at origin? Please see here. There's a shortcut for it. What I will do, equate the lowest degree term in the curve equation, to 0. To 0. Let me consider an example and show. I have an example like y square into a plus x is equal to x square into 3a minus x. Okay. Yeah. How do I know what is the lowest degree term? I will be expanding it. Ay square plus xy square is equal to 3ax square minus x cube. Okay. Now, just see here. Please focus here. What that is. This is a third degree term. This also is a third degree term. Now, coming to this one, it is second degree. This also is second degree. If I put them in one equation format, ay square plus xy square minus 3ax square plus x cube is equal to 0. If I club the second degree terms together, I'll be having a into y square minus 3x square is equal to 0. This is my lowest degree term. I'm equating this to 0. So what I will be getting? Y square is equal to 3x square, or y is equal to plus or minus root 3x. Okay. Now, look here. There's an important point here. Just a second. So, see here, there's an important point to be noted, which is very, very, very important. What that is here, what are the roots that I have is minus root 3x and plus root 3x. Okay. These are, just see here, I will make a note because this is very much important for the basic shape of the curve, that is real and distinct, different roots I have. Okay. So, what it conveys to me here is the curve has a node at origin. Node and origin. Okay, what's the node? Let's see what's the node. If you understand this, half of your job is done, guys. Okay, what's the node? Let's see here. Node is nothing but the curve has to trace that point twice. That means what? For which it has to crisscross. Now, how do you know that it is landing on x-axis or y-axis, or negative x-axis or negative y-axis? How do I know this? This will be decided by, again, please note, I'm writing it, which is very important. This will be decided by intersection. The point intersection, the checklist intersection with the axis. Okay, finding out intersection with the axis is very simple again. Okay, but then please remember the curve has a node at origin. Why? Because the roots are real and distant. Okay, coming back to what I was doing prior. Now, I'll take one more example. There's one more example. Of course, it's there here, I think. Yeah. There's one more example. Y square into 2a minus x is equal to x cube. Now, what I should do? The lowest degree term in the curve equation. What's the lowest degree term? Lowest degree term, just see here. This is third degree. Okay. Of course, y square is second degree term. Okay. So that term I'll be equating to 0. Okay. Lowest degree term would be y square into 2a minus x. Of course, I can expand this as well, guys. Just see here. 2a y square minus xy square is equal to x cube. Okay. Now, if you look here, xy square is a third degree term. X cube is also a third degree term. Only this one is a second degree term. So what I can do is, just a second. 2ay square, I'll be equating it to 0. So y square is equal to 0 implies y is equal to 0, 0. Please observe here, again, this is an important point. Y is equal to 0, 0. I have them to be real and repeated. When I have real and repeated roots at origin, then the curve has a cusp. Curve has a cusp at origin. As is, anything is fine, but it has a cusp. Now let me show you the basic shape of the cusp. Okay. Yes. See, cusp means what? Something like this. Okay. Now you can ask me, ma'am, why is it towards x-axis? Positive x-axis. No. It can be towards negative x-axis. It can be towards positive y-axis. Okay. It can be towards negative y-axis as well. Then how do I decide? How do I decide about which axis it is there? I will decide this depending on the asymptote. Now here, what I am telling you, when I have a node, intersection is very much important. Here I have written it, right? When I have a node, when I have a cusp, asymptote is important. Asymptote decides how my curve should be. Okay. Yeah. What will decide? Again, I'm writing it in red. Asymptote will decide the alignment. Asymptote decides the alignment of the cusp. Alignment of the cusp. So, without loss of generality, let me finish with the asymptote first and then skip to different things. Intersection with the axis, which is very simple. Okay. Asymptote. What is an asymptote? See, here I will tell you, please check the definition of an asymptote as well the definition of oblique asymptote. Okay. I will anyways talk about in the problem, but then please check the definitions of asymptote and oblique asymptote. What is it? A simple definition I will give. It is a line. It is a line which appears to intersect with the curve at infinity, which is a very basic definition. Please look at the standard definitions. Standard definition of an asymptote, which appears to intersect the curve at infinity. Okay, all of us know with our basic classes, knowledge, foundation classes, knowledge. Now, how do I find an asymptote parallel to? There are different types of asymptotes, by the way. Or 3 types we'll be discussing here. Parallel to x-axis, asymptote parallel to x-axis, we will be discussing. How do I find? For any asymptote, what I have to do is, please remember, equate, again, this is a shortcut, equate the highest degree term coefficient of highest degree term, what I want, parallel to x-axis, highest degree term of x, coefficient of highest degree term of x to 0 I will do for a asymptote parallel to x-axis. Now, if I consider this equation only, guys, this equation, what was that? I will just write here. Let me check. Let me show you. Y square into 2a minus x is equal to x cube. What's the highest power of x? In this equation, it is 3, right? third degree, right? Now what I should do, the coefficient of highest degree term, I have to equate to 0. That's the shortcut. So what I will do, coefficient of x cube is what? Coefficient of x cube is what? 1. 1 I'm equating it to 0. That is the sense. Is it sensible? No, senseless. Hence, or I will say not senseless, contradiction. It's a contradiction. So what I will conclude here, no asymptote parallel to parallel to x-axis is what I will say. Okay. Now, how do I find an asymptote parallel to y-axis? Same criteria. Equate the highest degree coefficient of x term to 0 in the curve equation. In the curve equation. Okay. Equate the coefficient of highest degree term of y term of y to 0. Okay, consider the same example. Consider the same example, please. What's that? Y square into 2a minus x is equal to x cube. Of course, in the equation of the curve. In the equation of the curve. Okay. Now, what's the highest degree term of y? It is 2. Okay. Second degree term. So what's its coefficient? Its coefficient is 2a minus x is equal to 0. So this implies x is equal to 2a. Now see, there are some things which I have already found about this curve. Please see here, this curve passes through origin. First thing is that. Second thing is, this curve has a cusp because at origin it has real and repeated roots. So this curve has a cusp. So I can easily draw the curve now. Please see here the graph. See the graph of the curve. Graph of the curve. Okay, what's it? Please see here. Okay, this is my x-axis. This is my y-axis. Yeah, x is equal to 2a. Would be where? X is equal to a. X is equal to 2a. Okay, and I'm saying the curve has a cusp. Okay, at origin. So this is my line. X is equal to 2a. Okay, so cusp would be something like this. Okay. Of course, you can ask me, ma'am, how are you deciding that the cusp is inclined like this? There are other different criteria with which I will conclude saying the curve would be exactly like this only. But then basically with the basic knowledge of 2 to 3 things, I should be able to trace the basic shape of the curve. That's my motive here. It's a shortcut. So these are all shortcuts. So I'll be deciding like this. Now coming to the node also, please guys, I will consider this very same example where I said that there is a node. Okay, what was that example where I said there is a node? This is the example. What's it? Y square into a plus x. Y square into a plus x is equal to x square into 3a minus x. That's my curve equation. I will just show how will I find the node. For the node, I highlighted the important point that you should know the intersection, right? Yes. Now, there's one more criteria. Let me finish it off. There's something called an oblique asymptote. Oblique asymptote. Definition is very simple, guys. An asymptote which is neither parallel to x-axis, which is neither parallel to x-axis nor parallel to y-axis, parallel to x-axis nor to y-axis. Y-axis. It looks like an oblique. Okay, but usually for house numbers and all we'll use oblique. It looks like an oblique. Okay, I will talk about how to find an oblique asymptote. I as well considered an example where there's an oblique asymptote in the beginning of this session. You can just rewind and look back. Okay, now look at this example, please. Okay, yes. Now, I have, of course, before going to this example, I'll finish off saying how to find intersection. You are all aware of how to find intersection, guys. It's very simple, very easy. How do I find intersection? Intersection with the axis. It's very simple. What that is See, in your basic foundation classes, if someone would have asked you to plot the line x plus 3y is equal to 6. If they have asked you to plot this, what you would have done? Or 2x plus 3y is equal to 6. If you ever asked to plot the straight line, what you would have done? First thing is put x is equal to 0. Then your y would be what? 6 by 3, which is 2. So the point is 0, comma 2. Okay? Yes. Next, put y is equal to 0. And then x would be what? 6 by 2, which is 3. So the point would be what? 3, comma 0. So how do I plot this? This is x-axis and this is y-axis. Okay, 1, 2, 3, 1, 2, 3. Okay, now I have the point 3, comma 0 here. I have the point 0, comma 2. I'll be joining these two and then I'll be getting the line 2x plus 3y is equal to 6. Okay, similar criteria is followed here. Not a big deal, not a confusing thing, not a rocket science. Intersecting with the axis. What I will do to put x is equal to 0 in the curve equation, in the equation of the curve to find intersection with y-axis. Intersection with y-axis. Okay. Yes. Next what you do? Put y is equal to 0 in the equation of the curve to find intersection with the x-axis. Intersection with x-axis. Fine. Okay. Let's take an example and check the same thing. Okay. Example. Y square into a plus x is equal to x square into 3a minus x. What I should do? Put x is equal to 0. If I put x is equal to 0, what I will be getting? Y square into a plus 0 is equal to 0. Right? Or y square is equal to 0. Y square is equal to 0. This implies what? The curve intersects y-axis. The curve intersects y-axis only at origin. Y is equal to 0 means what? Only at origin. Okay. Okay. Next, what I should do to find the intersection with y-axis, with x-axis, put y is equal to 0. If I put y is equal to 0, LHS would be 0. RHS would be x square into 3a minus x. Okay. I'll be having x square is equal to 0 or 3a minus x is equal to 0. Okay. This is what x is equal to 0. One more thing is x is equal to 3. So what I will have? The curve intersects the curve. What I will write? Intersects x-axis at origin and at x is equal to 3. Okay. Now, first thing is I know that the curve has a node. Please rewind and check, guys. Y square is equal to 0, y is equal to 0, comma 0. I'll have, I'll be having tangents at origin to be real and distinct. So I'll be having a node. Okay. And then it is intersecting with x is equal to 3. Now I will also find asymptote for this curve and then I'll be done. Asymptote, how will I find? Asymptote, how will I find? First, parallel to x-axis, I will check. Okay. Yes. Parallel to x-axis. What I should do? The least degree term of x. I will have highest degree term coefficient of x. I will equate to 0. Ay square plus xy square is equal to 3ax square minus x cube. X cube is the highest degree term. So its coefficient would be what? 1. Okay. So 1 is equal to 0. This is contradiction. So no asymptote. Okay, parallel to x-axis. Now parallel to y-axis. Y-axis, how will I find? Highest degree term of y is highest degree term. Highest degree term of y is what? Is y square. Coefficient of y square is what? Is a plus x. I'll equate this to 0. So I'll be getting x is equal to minus x. This is my asymptote parallel to y-axis. Asymptote parallel to y-axis. If you have an asymptote, please highlight it. Asymptote parallel to y-axis is x is equal to minus x. Now, I know that it is a node, and I know it is intersecting with the x-axis at x is equal to 3a. This is a, this is 2a, this is 3a. This is my y-axis, this is my x-axis. This is x is equal to minus a, this is a, 2a, 3a. Okay, so just see the node should be something like this as, okay, now there's an asymptote. So the curve can't go beyond the asymptote. Okay, just a second. I'll draw it again because it is very huge. The shape is going out, but then basic shape, I think you understood by now. Okay, but this is a, this is 2a, this is 3a, this is x is equal to minus a. Now this is my line x is equal to, okay, so at this asymptote, the curve will be there. Okay, it is as if the asymptote and the curve are meeting at infinity, and intersection with the x-axis is at x is equal to 3a. Okay, I think I am clear. I think you now you understand what are the points that you should focus on. Okay, yeah. In the next lecture, I will solve an example and show how one complete example, how you decide the remaining things. I'll consider a different example and show you. Okay, asymptotes. Now, of course, there are other points like R. R is the region in which the curve doesn't lie, region in which these are all secondary lines. Okay, those are just for cross-checking. Curve doesn't lie. This is okay. Okay. Also, there's something called T, another T, which is tangents. Tangents at a point which decide whether the curve is concave or convex. Tangents, they can be tangents, they can be table also. I can construct a table for all x and y values, x and y values. Okay. I can construct a table for different x and y values. How that x and y values should be? There should be a 0. There should be some negative values. Okay, there should be some positive values. Okay, why? Because the curve changes from convex to concavity. Okay, so accordingly, you can use tangents at any point. At any point you can find by going with dy by dx and d square by dx square. Okay, this way I can find out, or I can construct a table as well. Region in which the curve doesn't lie, how do I find this? For whatever values of x or y. See, R, how do I find? Let me just finish off this session. R, how do I find this? For some x values, y becomes imaginary. Becomes imaginary. Okay, similarly, for some y values, x becomes imaginary. I omit those values or those regions. We omit those regions of y or of x or y values respectively, of x or y values. The region in which the curve doesn't lie is what I will check for, and I will justify my answer. Okay, I hope I am clear with this basic things, guys. I'll just give a repetition. Please listen here. Symmetry. First thing is symmetry. Symmetry is very simple and very trivial. What is very important is whether the curve passes through origin. If the curve passes through origin, then tangents at origin are very, 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 very important because they decide the basic shape of the curve. Then once I know the tangents at origin, I can as well find whether there are asymptotes or not. If I have an asymptote, then accordingly I will decide the shape of the curve or the inclination of the curve. And then I will decide whether the curve is, checking with this criteria, I'll decide whether the curve is intersecting with the x-axis or negative x-axis or y-axis or negative y-axis. Okay, remaining things are just to follow. Just they are for namesake kind. Means like I will check whether the curve is increasing or decreasing. Okay, looking at the tangents. Or I will justify saying that the curve doesn't exist because y values are imaginary. I think this much is enough. Please rewind and listen to it so that you will understand. I will as well share the notes along with this video. And then I will just do one or two complete problems so that you get an idea of curve tracing and Cartesian. Thank you. Thank you so much.